I see. You found your way in. Good.
We did.
Yes,
Thank you.
thank you.
Thanks for your help. everybody. Welcome to the Physics with a Bang. This is our 12th year.
So, I'm Heinrich Jäger.
I'm Sid Nagel.
Welcome to the show. Let's start it with a bang.
Are you ready? Yes. Okay. So, okay, get ready. Here it goes. Oh! Is that good? I need another. Are you ready? Do you want to hear it again?
Would you want to see another one?
Okay. Are you ready?
All right.
So one of the things that we have here is that you probably heard something, but you probably was too quickly for you to see something. And we have our high-speed camera operators, Nidhi and Jayi. Let's give them a hand. And they have filmed this for us so that we can see this in slow motion, what actually happened.
So here you see, first thing that happens is the balloon cracks. Just a little bit later. And then there's the explosion coming up right now. So, Nidhi, how many frames per second did you?
This is 4,000 frames per second.
4,000 frames per second played back in slow motion for you. And this is basically what drove that Big Bang.
Okay, so the next thing we need is, if we can, could we have a volunteer to help us? Okay, would you come down here, please? And we're going to need you to help Heinrich light this fire over here, but you're going to do that by working over here with Heinrich.
So, look, we're going to light this thing up from all the way over here by turning on this light bulb, and that's what you're going to help me with. Can you turn this dial slowly up? Turn it up, yep, a little bit more. That's slowly, slowly, slowly. And you see how this becomes light there?
So if you look over there, see the light is coming from there to there.
Slowly, slowly, slowly. Yeah, good. A little bit more, a little bit more, a little bit more, just a little bit more. See what happens. Oh, stop. Oh, what happened? Something got on fire. Let's do that again. Wait a second. So, let's see here. Try that up again. Not all the way, just a little bit. Do you know what? We might, now that's probably enough, you know. We might have burned it out. Oh. Okay. Help comes.
Here he comes, to the rescue.
Turn that back down. Okay, so now bring it up to about 80 and see what happens. Like this, like this. A little bit more, a little bit more. Yeah, even more. Go, keep going. Yeah, let's see. Whoa, look, it's really bright. Ah. Well, maybe we need some help there, Sid, with a match. What do you think? Hey, are you trying to light the string, Sid? Let me help you. Right here. You want the string, right?
Yeah.
There.
There we go.
Okay, come on here. There is the band. Well,
Okay.
let's give her a hand. Let's give
So
her a
let's
big
give her a
hand.
hand. Thank you very much. So how many of you play a musical instrument? Oh, a lot of you play musical instruments. Okay, so what do you have to do if you play a musical instrument? Well, you have to, well, practice, but also play in tune. But you also have to get the beat right, right? So you have to get it on the beat. And so that's what your music teacher tells you how to do. And so what they tell you is to practice with a metronome, right? So the metronome gives you that beat, and so then we know what's going to happen. So we have some metronomes here. And so if I start one of these metronomes, that's how you know what the beat is. But if one metronome is good, well, 2 must be better, and 3 must be better than that. 4, 5 metronomes. Oh, that's not so good. I mean, I can hardly hear anything. I mean, it's, how could you have a beat to that? So what we'll do is we'll try to make 5 better than 1. And so we're going to take these metronomes, and we're just going to pick them up and stick them onto this
Set of 2 round cylinders. And listen what happens.
There it is. And if we take it off of there,
After
they
a
go
while.
back out of phase again. So once you have, it's always nice to have a little some refreshment while you're playing your musical instrument, and this is why.
Okay, but one other thing that you probably know is that airplanes fly, right? And they do that, amongst other things, other reasons, for something called the Bernoulli Effect. Sid is going to demonstrate that.
So if I take this sheet of paper and I blow over it, you would think I'm blowing things out of the way. But it also makes the air go faster here, and that lowers the pressure. And so we're going to see if we can't bring this paper up into the beam of where I'm blowing.
Very
So
nice, Sid.
that works.
Very nice.
It's kind of
But,
pathetic.
well, give him a hand. But this is... I think we can do better than that, right?
I think so. Maybe we should do it industrial style? Okay, so we'll do it industrial style. Okay, so here we go. Here is a sheet of paper. Here it goes over the sheet of paper. And now we...
See?
So we...
It tried to fly off.
What else could we do this with?
Let's see what else we can try to make fly.
Okay, so
We're
let's
gonna
see what we
blow
can
over, right? Over this
do.
thing?
Over the top.
Yep.
Where's the lighter?
So that was pretty loud, and now we'll do something a little bit more quiet. We're going to show you what sound actually looks like.
So we have a tube where he has the gas going through this tube, and we've lit it on the top where little holes are, and you can see that the gas is coming through those holes, and you can see how it lights up into these nice, beautiful flames for this time of year, which is rather beautiful. So we also have at this end a speaker.
And so we can pump some sound into this tube. It's like blowing into a flute.
And so the speaker at this end, we're going to put a note on, and we're going to see what happens to these flames. Yeah.
You should know what this is. So that was a very nice sound, and it was a beautiful sound, and it was still a relatively quiet sound. But you know, sound can also do something really more dramatic. Sound can put a lot of pressure onto objects. And one thing that we're going to try now is to use sound to break a wine glass. This is a real wine glass. And
it's real sound.
Real sound, and it's going to be real loud, because you can imagine that you need a lot of very loud sound to break.
He'll tell you when to do this, but be ready to stick your
We'll let
fingers
you know
in
when it, and you'll find out when it gets loud. And you know, because wine glasses, when they finally break, they break really quickly. You may not be able to see that with your eyes, and so our video team is filming it at some very high speed, and then we play it back in slow motion. But I think what we'll do is we'll already show you what they see now. Is that all right, Nidhi? Shall we do that? So I'm unblanking this, and you can see what the camera sees right now.
So you see the top of the wine glass, that's what you're looking at.
See the rim of the wine glass right there. And now, well, start up the sound. You might want to put your fingers in your ears. So let us introduce actually Andrew Nailman, right here. All right, so let's wait for this to be spooled back, and then we will show you what happened to that wine glass. Are we ready, Nidhi? Not yet. Okay, so we'll set up the next experiment, the next demonstration, and meanwhile go back to the tape here. And if you look now, you see what happens to that glass in slow-mo. And right now it's breaking into pieces. By the way, this is something you can only see right here. This is research-grade video that we also use in our experiments. Very fast, and these are very good low-light cameras. Yes, you can try that at home.
You have to hum very, very loudly at the glass. Okay, so this next demonstration is to show you to be careful. Okay, so what I've done with this is I took some of this liquid, it's alcohol, and I poured it into this big water container, and I'm turning it around and around and around, and I've got to do this for a while, so I have to tell you a story while I'm doing this, so we don't all get bored. Okay, so I'm trying to coat the sides of this with that liquid. And there's a wonderful YouTube video that you can look up about this person who comes into a gas station in the middle of winter and sticks the gas hose into the car and is filling the gas tank. But because it's winter, they go back into the car and they wait there until the gas tank is filled. And then when the gas tank is filled, this person gets out of the car and they go over to the gas handle and they make the mistake of touching it. And at the moment that they touch it, the whole car bursts into flames. And the point of this is that they had a little bit of static electricity on their clothes after getting to the car, and it rubbed with the car seat. And as it rubbed with the car seat, they build up static electricity. They had a little bit of a shock as they touched the gas handle, and then the rest is history. And of course, what's nice about the YouTube video is everyone was okay at the end of it. So, but nevertheless, it was obviously a dangerous thing. And so we're going to try and show you what kinds of things can happen here. And so I think this is now basically ready. Are you ready, Nitty?
Pretty much. Wait.
You ready? Okay, so I'm now going to just take a lighter at the top of this and see what happens. What did I hear? Okay.
All right.
So that's what can happen if you're not careful, and if it's not contained, you could tell that would have been
Right.
bad. And so I'm just going to non-contain it now.
Well, so let's see. So that was very nice. It was this way, right? But what if we just turn this around a little bit? Let me try that again. So let me put the gas tank this way. Okay? All right. Yay!
Bravo. So, Nitty, are you ready to? We can show you what you saw very quickly on this can and see how that took place.
So it lights at the top, and then you see the flame front moving in, slowly engulfing everything, and then starting that whoosh that you heard. All right. Thank you, Nidhi and Shayi.
Okay, so what we wanted to show you now was a little bit of optics, and so this is just an ordinary container filled with a liquid, and what we're trying to show you here is the thing that you probably have seen a whole bunch of times of we stick a rod into this liquid and it looks like it's broken as it goes into the surface, right? That is it, because as you look in, the rod seems to be in a different place when you're looking at the side than it does when you're, then it's out of where it would have been if we just stuck it in. And so this is clearly something that happens because this liquid has something what's called the index of refraction, which is different from air. And so as you go into this liquid, it looks like the rod is bent, even though it's not bent. And so this is one easy thing to show. And so I'll take this rod out. And so now we have this clear container.
What else can that do?
And so what I want to, pardon?
What else can this do?
Well, what else can it do? Well, this is a circular container, so it's kind of like a lens. And so, can you read this? Well, it's kind of, I can't read it. It's kind of weird. It's gabang or gnab or something like this. And so what I want to show you is if I pass it behind this container, we'll see what happens. So you can see that it reflects it or brings it to you, but in the opposite. It reverses the direction of this thing. So it's like a lens. And so in your good optical quality microscopes or telescopes that you have, that's why you always have two lenses to reverse it once and then reverse it again so that you get back into the direct way that you see it. So this is reversing the direction. Now, this is one thing that this liquid can do, but there's another thing is it's actually a very magic liquid. And so what I have here is a glass tube, right? Everybody can see it's a glass tube. And so I'm going to take this glass tube and I'm going to stick it into this container, right? So there's this little Ziploc bag. And then what I'm going to do is I'm going to take a hammer and I'm going to smash it. So I ask you to all, is this smashed? Yes? 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 Okay. Well, yes? Okay. We all agree that it's smashed. Or those of us who have seen it agree that it's smashed. Okay. So now I'm just going to pour this smashed glass tube into this container of magic liquid. And I'm going to say we're physicists, therefore we can do all sorts of things. And so we're going to see what happens here. And so I take this, that thing was all smashed, and now it all comes back together again. Okay? And so, of course, this is not magic liquid. It's just ordinary liquid. And what we've done is that if you look at this tube, as I push it back into the container, it looks like it disappears. And the reason for that is because that thing I told you about at the beginning, the index of refraction, is the same for this glass as for this liquid. And so that's the only thing special about this liquid is we made the liquid to have the same index of refraction as this glass. And so that's why this works. And it hides completely, and the broken glass is at the bottom, and I'm not going to stick my hand in there to show it to you. Okay, so I hope you will believe that. Okay, so that's one thing this liquid can do. But now I want to show you something else that you can do with these liquids. And so I have here a cylinder, a plastic cylinder on the outside, and I have a cylinder on the inside, and I can turn this cylinder around and around with this handle on top. Okay, so I can just stir this up, and between these two cylinders I have liquid. And so you can see as I turn it, it mixes it up. Well, you can't really see it because there's nothing to see. It's a clear liquid. So what I'm going to do is I'm going to now put some dye in it so we can see what's happening to this liquid. Okay, and so here is my dyed liquid, and I'm going to stick this into this little hole in the top.
We should maybe say that that liquid that's in there is the same liquid that you just saw before. It's that clear liquid. It's just the inner cylinder is white.
That's the inner cylinder is white. Okay, and so here I'm going to put something in so we can see what it is. And so I'll put an S for science. So science is really strong, and so I can't make science disappear, right? That's clearly, I mean, so that it will never disappear because science is real. Okay, so now let's turn this and see what happens.
Uh-oh.
I guess science wasn't as strong as I thought for a second there.
But what about physics? Maybe
Okay, so let's try it with
physics.
physics. Let's try put a P in for physics. Okay, so now let me put that in. So here is a P. There's the, and so here is,
Can you all see that?
okay, so you can see that there's a P standing for physics. So now we're going to see if physics is going to be strong enough to withstand mixing, okay? So I will twirl this again. Oh no, Heinrich, it didn't work. So let's just keep mixing it and see what happens. And so I keep mixing it, and it's just messed up. It's just mixed all together. And we know that, I guess we should have expected that to happen, right? So now I'm going to keep turning this and see what happens. So I'm going to keep turning it and see whether, as physicists, we're strong enough to reverse time. That's the idea. So we're going to try and reverse time here. And I keep turning this thing, and what happened there? So physics came back. Physics was strong enough.
All right. Wait, but what about science? What about science? Do
you think science is strong enough to come back? So let's see whether science comes back. So science and physics both came back. And so clearly this was not a magic fluid anymore. This was just a demonstration of one of the theorem in fluid mechanics, which allows us to say that if you are very careful in designing something, you can actually make the liquid not mix at all, but bring it back to where it started from. But it's a very anti-intuitive behavior.
So now the liquid that Sid just used was, wasn't water. It was glycerol. And so what I'm going to do now is I use just water, but I put a little bit of stuff in there, small particles. And so you see this thing here is now milky looking. See that? Like a liquid. Maybe in the front row you can see that. But the question now becomes, can you walk on water? No, of course not. But can you walk maybe on this milky liquid? Does something happen to this liquid? So I'm not so sure, so I better put some boots on here. What do you think? Can I walk over this? Yes. Really? Okay, let's see.
Oh, that's amazing, Heinrich. What's he doing?
I mean, you think I can just jump on this, huh?
Oh, there's no water in it? You think it's just nothing's there, so.
But it is a liquid. Okay, so let me now just get out then. This is a funny liquid, isn't it? It's actually pretty strong. Look at this. So this liquid, this crazy liquid, fluid, I should say, maybe it does other things too. Maybe, what do you think? Is it good for absorbing energy?
Well, I don't know, but there's something here that there's a tank that looks like it's full of that same stuff, Heinrich. What are you going to do with it?
It's the same liquid, right? Okay, so let's see if it absorbs some energy. Let me drop something in there. I don't want to jump in it. We'll do better than jumping. We'll just drop something.
Are you ready? I mean, I would cover yourselves up. I would just.
So, what do you think we should drop in there? Something nice and fragile? Oh, no. some.
What do you have in your container? What?
I think we should put an egg in there. I think an egg is nice and fragile. And this crazy fluid, maybe it'll, I mean, if I drop this on the floor, right, it'll.
Then I would get it out of there if he's going to drop it on the floor.
So let me just drop this in there and see what happens.
Uh-oh. Well, look at
that.
this.
The egg survived.
It didn't break at all. Well, you know, my guess is that he faked this. This is probably a hard-boiled egg, right? Well, someone help me test whether it's a hard-boiled egg? Okay, come on down. And so what we need you to do is more or less gently take this and just push it up, smash it against the wall. Throw it against the wall a little bit, but not too hard. So, not so it's just to see if it's. Yeah, it is. It's a real goopy raw egg.
Yes, yes.
Okay, let's give him a hand. Thank you very much.
All right, all right. Somebody said bowling ball? Should we just throw a bowling ball in there?
Heinrich, you can go higher.
Okay. Higher?
What do I get? Higher? Okay, so let's see what happens to this. Are you ready?
So, just one thing, if that would have been water, you'd be wet, right? So this is a hell of a special liquid. Ooh, look at that. All right. So, what this was is actually small particles in the liquids. It's really something you can do at home, or you can do later in a demo alley, is these particles happen to be cornstarch. Could be other particles, but it was just cornstarch in water. So, look, there are all sorts of interesting behaviors with liquids and particles. But liquids as well as gases are called fluids. It's just that the fluid is less dense, less concentrated than an ordinary liquid. And so the next experiment kind of relates to this whole theme, but the fluid is going to be a gas.
Okay, so what we're going to try and do here is we're going to try to float a boat, right? And this is clearly a boat because it says boat. It says boat, right? So we're going to try and float this boat, but we're going to need a volunteer to come down and do it. So, yeah. Hey, okay. And so what we need you to do is to make sure that we're being honest, right? So that's the idea. So you have to tell us if we're faking at anybody. And so what I want you to just check is, do you see any liquid in this container? Can you just make sure there's nothing in there? No. So say that loudly.
No.
He said no. Okay. So there's no liquid in this container. And so what we're still going to try and do is float this boat on gas. Okay. And so that's the idea here. And so we're going to just let this go for so we're filling this up with gas, but it's not liquid, right? There's no liquid coming into this. Okay. So
what do you think,
go.
Sid? Looks full to me.
Okay, so we're going to very carefully remove this cover. Oh.
Right.
Yeah. Be careful. Okay, so now we're going to try and take this thing, and I'm going to try and let this thing
I don't
float
know
on
if
here.
that can work.
And is there any liquid in here?
No.
No. He says no. So there is no liquid in here, but it is just floating on gas. This gas is a heavy gas that we put in here. It's called sulfur hexafluoride. And so it's a heavy gas, and so this boat can float on gas even though it's not a liquid. So it's heavy enough to float this boat. And to see how we could empty this, so let's try and fill this container with
Oh, that's one good boat.
this is a good boat.
Ah.
Okay, so let's give him a hand. Thank you very much.
Okay. So, talking about fluids that are just gases, right? So the air that we breathe, that's a gas. You can hear me because sound goes through that gas. This is a drum. You can hear that. You can feel it. Can you? Yeah. Air, but can you see it? No. So let's see it. Let's
Okay,
see if we can
Yeah,
see it.
Go ahead. You want to turn the lights down a bit?
Yep.
Okay,
So we put a little bit of
watch
smoke
what
in
happens
here.
here.
Okay. Okay, so Sid told you about what's called the Index of Refraction, right? So in other words, if you send light through something like glass or liquid, it gets bent. And if you send light through air, it also can experience a change. And this is a very, very sensitive instrument where, in fact, the tiniest changes in the air can change what you detect on the other side. In fact, we make these changes so tiny that even if you make the air just a little bit warmer, you see a change.
That's right. But we need a volunteer from this side this time. Okay, so why don't you come down here? I can't, it's too dark for me to see, but I saw someone, I saw a hand. So you come on down with your hand. Now, we want to make sure that you're warm. It's not too cold in here, right? Okay, and so what we want to see is if you put your hand in here, can you see the heat coming up from your hand? Whoa, you are alive. This is wonderful. So this is good. And not only you're alive, you're a warm-blooded animal. This is wonderful. Humans are good. Okay, so we're able to see this, and now if we do this with a lighter, we can see. You can see all of the heat coming out of this and how it rises. And now we're going to ask you be careful because this is very cold, but if you can hold this up near the top of this. So this is dry ice. And now you can see that the heat it's colder than the rest of it. And so now the cold is falling down, and you can see that. Do you want to try that? But it's a little heavy, so be careful that don't get your hands. Great. So just put it near the top. Right. So you can see now the cold stuff falls down, but when she put her hand in, that's great, thanks so much. When she put her hand in, it rose. And so let's give her a hand. Thank you very much. So this is what you see on a hot day in summer. I don't know if you remember summer, but there used to be summer here. And on a hot day on a highway where the heat is baking down, you can see little plumes of heat coming from the highway. You can just barely make it out. That's what this optics was able to do, was to magnify those little changes in the index of refraction between hot and cold air to make it visible for all of us to see.
I think it's time to crank up the danger level a little bit. Sid, let's do something more dangerous.
More dangerous? Mm-hmm. You want me to do the more dangerous thing? Uh-oh. So, well, what is this? So this is a bowling ball, and a long cord is holding it to the ceiling. So this is just a pendulum that will go back and forth. And so, of course, we know that this pendulum is never going to rise higher than where it starts, right? Because that would violate laws of physics, and laws of physics never get violated. And so we're going to show this here. And so to show this, I have an egg sitting here, right? And so I'm going to put this next to the egg, and we're going to see that this will certainly not come up and break the egg, right? So this is... Uh-oh. Uh-oh, okay. So... Okay, so maybe physics isn't always right, but most of the time it's right. So I'm going to try it again. It couldn't happen twice wrong in the same thing, right? So I'm going to do this again. I'm going to do it so that my nose is there instead of the egg.
I think that's a great idea.
Okay, so...
it's going to be the ultimate test.
Okay, and so I'm going to put my head up against the wall so I cannot move my head, okay? So, and my nose cannot move around my face usually until after the ball hits it. Okay,
that's too dangerous. You know what? We can't let Sid do that. You just saw what happened to the egg. That's not right.
I'm going to do it anyway.
Are you
I
sure?
believe in physics. Okay, so here we go. So are we ready? So is it up against my nose? Okay, so here we go. I'm going to let it go and see what happens. Okay, and so what just happened in front of your eyes? We were able to show that this didn't go higher than it was, but why did it go higher the first time was because I pushed it a little bit. So it wasn't, I knew what I was doing. I wouldn't have done this otherwise. Physics is always right. It doesn't sometimes work and sometimes not work. When it works, it works. And so that's why I believed in it. So now we're going to do something really dangerous. And it's going to be just slightly noisy. Okay, so you're going to need to put your, ready to put your fingers in your ears.
This is really quiet experiment now. Very quiet, right? You know what this is? You know what's in there? All right, let's see what happens when it comes out. It goes probably in this direction. All right, ready?
Oh my God! Well, it seems like we had a little accident backstage. We're going to have to take Heinrich to the hospital, so we're going to ask Nidia Jai to continue on with the show to help us out. Could you do that for us? Okay, so we'll try to be back.
Yeah. Well, hi everyone. Looks like Heinrich has to go to the hospital, but he'll be okay, and we'll take care of the show till then. So.
What do we have here?
Well, what I see here is a copper tube. It's a big hollow tube. Can you see that? Yeah.
Okay.
What do you have, Jai?
So I have a copper block.
Oh, yeah, it's a little block.
It's not magnetic. Oh.
Okay.
So can I put my copper block into your copper tube?
You can do that. It's a tube. It will fall through. I don't think
try it.
there's anything interesting going on there.
Let's try it.
Okay, sure, let's try it.
Oh,
Sure, yeah, that's what everyone expected, right?
okay.
Do you have anything else?
I have magnetic one here.
Well, okay, but copper is not magnetic, so it's not going to do anything.
I bet it's not.
Okay,
Let's try it.
Sure, let's try that. Oh, it's falling really slowly. I think it's still in there.
Really?
Yeah,
It's not disappearing?
no.
Oh,
Whoa. Wow, what happened there?
I think this copper tube created a current that hold this magnetic disc, so prevent it to fall down.
Oh, that's interesting. So why do you think that happened? Is that because copper is a conductor?
What is a conductor? You mean a music conductor?
No, not a music conductor.
Oh, you mean a train conductor?
No. I mean a conductor of electricity, something that lets electrons flow through it at really high speeds.
Oh,
And copper is a good conductor of electricity, and I bet that happened because copper is a conductor.
I see. So, conductor of electricity.
Yeah.
So in here we have a superconductor.
Oh yeah, so what we have here are pieces of crystals that become superconducting when you cool them down with liquid nitrogen.
Okay.
So that's what we are going to do now.
How
We have
does
some liquid nitrogen here, which is really cold, and we put it in this container.
oh
Yeah, and now we put our superconducting pieces in there. So here's a piece of superconductor. I put it in there.
okay.
Yeah, we let it cool down really nicely, because once it cools down, it will be superconducting. So what do we have here?
So here is the magnetic train rail. You can see.
Oh
So
yeah.
what are we going to do with this?
I think if we put our superconductors on top of this rail, it will float.
Oh,
Would you like to see that? Yes. Okay, let's see. So our superconductor is now nice and cold because of all the liquid nitrogen.
ooh.
Yeah,
Is it really floating?
it is.
I'll put the paper in here. Ooh.
Yeah, it really is floating. Yeah. Would you like to turn it upside down? Do you think it will still float?
Yeah. But how about we do it in here?
Sure, yeah, let's try it there.
So here we have another train rail. But I'm going to put it in here. Yeah, on the bottom. Okay. So. Ooh.
Oh, look who's back. Oh,
So thank you so much. This is,
sure.
okay, so now we want to do something a little bit more with electrical currents, and so this is going to be an electric experiment. And
Sid, are you endangering yourself?
well, not yet. First, I'm going to endanger everyone, and then myself. Yeah, no, that's okay. I'll move forward. Okay, so what we would like to do is we want to start this, up, and see if we can't, Andrew, can we get the lights down? Yep. Okay, so, you're there, sorry. Okay, so if you can turn this on, Heinrich, and let's see what happens. So can everyone see this thing is just sparking like mad? We can make it push it even farther apart. And if you look at what I'm doing, I'm just pointing at this thing, and I can make this thing stop, or go, or stop, or go, just by pointing at it. Can you turn the lights up just a little bit so we can see that? So where, see, as I point at it, it stops going, you go, stops, goes. Okay, so this is just a principle of Ben Franklin's lightning rod that you've heard of, that's just pointing at the sky with a grounded, sharp object. We can bleed the electricity off of the clouds. And so we're putting up a lot of electricity onto this, and that's enough to create these sparks, just as if you had a lightning bolt. Okay, so let's do something else, and let's see what kind of power we can have. And so I have here a light bulb, okay, but I have nothing up my sleeves, right? There's no wires here at all. And so I'm just going to hold this and see whether we can't get something interesting to happen. Okay, so Heinrich, can you turn that on? Okay, the force is with me today. Okay, so I can get this thing to light up even though I have no wires in my hand. Nothing is plugged into any outlet. It's just that the electric field from this dome is able to create enough field to get the currents to flow in this light bulb to make it light up. Okay, and so this is, the force, but now we want to do even more with the force. And so let me just get one thing.
It'll be a little transformation. You'll see. My colleague is transforming himself.
Okay. So here I am. And what I want to do is I want Heinrich to beam me up, okay?
Right.
And so I'm going to get on here and try to get myself up, but first maybe we should move this all the way down.
First of all, I think you might want to consider taking any metal object.
Oh, right. So I once did this with my glasses on, and I started getting sparks between my eyeballs and my glasses. And that was very upsetting to me. And I asked them to please stop right away, and we fixed that. So I'm going to take that off. And then just this time, while we were doing it, I started getting enormous shocks between this and me, and so I'm going to take this off as well.
Good idea.
And so now here I am. So I am going to try to beam myself up, and let me get as far away from the thing.
Danger. This is dangerous. Don't do that at home.
Okay. Beam me up, Heinrich.
All right. Sit.
style.
Give him a hand.
Now, how do I get down?
Well, first of all, it's too frizzy. Let's change that.
Okay, I feel much better now.
All right. So that was a lot of electricity here, actually. A couple 100,000 volts. And now what we're going to do is we take similarly lethal electricity, and we're trying to use electricity to cut right through a beverage can. Can you imagine that? So what you see right here is a can, beverage can, and it's inside a coil, and we run some current through that coil. We're not touching the can, we're just running it through that coil. But if you ever thought about taking a screwdriver to a car battery, you know that's going to be a bad idea, right? So here we have a 9,000 volt battery. That's that big silver thing right there. And we essentially put a screwdriver across it. In other words, we just run the current right through the coil. This could be a little loud. I will let you know. And it could be a little dangerous. I'm already, you know. All right. So are you ready? Because we want to film this. This is so fast also if it works that we want to film it. Okay, good. So I am now charging up this immense capacitor or battery, and I'm calling out the voltage, okay? Just so you know how dangerous it is. All right, it's 1,000 volts. 2,000. You want more?
Yes.
3,000. 4. You got 4. Anybody more? 5. Good. You got 5. Who wants 6? We got 6. Sold. Sold. How about 8? 8. You want 8? All right. Okay. 8.5. 9,000. You got 9,000. All right.
I think that's enough, Heinrich.
I think this is getting so lethal. Let's just stop at 9,000. I will now push the button. Are we ready with the video? Okay. 3, 2, 1. And there.
So you can see what happened. This thing just ripped in two. It squeezed down the middle and then pulled itself apart, and it's really quite
Anybody
hot.
wants to feel this thing? It's still warm. Kept it sharp. Okay, so let's see if we can play that back. One second. Don't hit it yet. I would like to. All right, so now here you see the coil, and we are playing it back. That was the flash, and you see how this whole thing crumbles and gets pushed apart just by the current, and then the current generates a magnetic field, and that in turn does more, and so the whole thing just comes together. It's actually a beautiful demonstration of what current and magnetic fields can do.
Great. So I don't know about you, Heinrich, but I feel like I'm under a lot of pressure these days. Are you under a lot of pressure?
Always. And in fact, you know, just being around is a lot of pressure.
Yeah. I mean, but how come we feel so much pressure, but we don't collapse?
Well, because we We pressurize our insides, don't we? We
Oh,
push
is that why I feel so much pressure inside?
That's also true.
Ah,
It's a nice balance, I think.
so you mean there's not much pressure on the outside as on the inside, and that's why we're okay?
That's right.
That's wonderful, but what would happen if we took the pressure out from the inside?
I think we would collapse, wouldn't
We
we?
would collapse and we wouldn't be able to really walk around very well anymore.
Not anymore.
So shall we see how that would work?
I mean, how much pressure do you all feel right now? It should be 15 pounds per square inch. That was not very scientific. 100 kilopascals, more or less.
So that's a square inch, and that's 15 pounds right there, down, but also there, up, so it's okay. But if we got rid of the air on one side, then it would really come crashing down.
So,
That's a big tank.
and what we're going to do is we're going to pull the air out of this tank. Now, this is meant to withstand a lot of pressure. But let's just see what the pressure you are under every day, 15 pounds per square inch, what that can do to a steel drum. This is the real thing.
This is a real steel. Okay.
Oh, okay, don't worry.
So far, so good. Okay, so now we continue to pull the air out, and
Well, I mean, it is a big volume to begin with, and it's also nicely reinforced drum, so I don't know if
yeah,
that's
they don't want these oil drums to leak.
correct.
We
All right,
hope.
you gotta be patient. Are you patient?
No, 100. I'm not sure.
All right, well, why don't we
Why don't we go on to the next
set
thing?
up the
and,
next experiment already?
Let's see what else we can do.
Oh! That,
Okay. So that's what can happen if you have the air out on the inside, but you have the air on the outside, and so this is now, instead of being a barrel, it's a sculpture.
Yes.
So this is the
It's a sculpture.
so now what we're going to do, we kind of repeat this idea of pumping out air, but we will pump out the air out of a vessel that we know will not possibly collapse. So this is now a tube, this tube right here. It is very thick wall plastic. Tubes like this do not collapse, and we will pump out the air, and we have it sealed at one end, and we have it sealed at the other end, and with fairly thick aluminum foil. So over that small cross section here, that area of the ends, you know, that's maybe 2 square inch. The aluminum foil can withstand that pressure.
And at this end, we have a ping pong ball. Ping pong balls are pretty wimpy, right? They can't do much damage to anything. And so you can pop it on the floor. It doesn't do much. I could throw it at someone and they wouldn't feel much hurt. You play with ping pong, you do it really fast, comes really fast, and it's not a dangerous game unless you get hit by the paddle, but not by the ball. So this is okay. And so what we're going to try to do with this experiment is we're going to try and get this ping pong ball into this can. So we're going to try and get it through this into the middle of this can. Are we going to be able to do that?
Really?
You say yes? Huh? Oh, well, we're not so sure. I'm glad that you have faith in us. That's good. But that's what we're going to try to do.
Right. So for that, I need to take this off. Oops.
So Heinrich is going to turn on the vacuum pump on that side.
Yep.
And he's going to suck out all of the air in this. And then when he's ready and we're down to low enough pressure, we're going to try and see if by punching that side, he can get the air to rush in push the ping pong ball in front of it and get it into one of the cans. Okay, so are you ready?
With the video?
Okay, so we're now at 5, 10, it's the other way, 15, 20.
You were right. It should go down, but this is upside down.
25, 26, 27, 28, 29, 30.
I don't know, Sid. I mean, no, this is metal.
It's metal, that's true. And it's a ping pong
This
ball.
is this little ping pong ball. I don't know if that could possibly work.
Well, we're only trying to get through those little holes on top, right?
And actually, you know that, right? We've never done anything like that before. This is really the very first time. This is the impossible experiment. You are witnessing history.
History right here.
I don't know.
Okay,
Should I
so
try it?
why don't you try it? Are you ready?
Okay. I'm trying to puncture this, okay?
But put your, this will be a little bit loud.
Okay. So here we go. 3, 2, 1.
So we did get this through them for a while, but it went through both
Look at
cans.
that. All the way through.
Both of them went through. And this is the ping pong ball that did the work.
So now that was somewhat fast, right? And that is because the ping pong ball got almost to the speed of sound, 2/3 of the speed of sound. And so we needed to capture that with a very, very fast video. And Nidhi, what do you think? How fast did you record that? So that is kind of the record here for us. This is 25,000 frames a second, right? And so now we're trying to show you this and play it back, okay? So before you start, let me turn the lights down a little bit. So here you see a close-up of the Coke cans. And again, you won't see that anywhere else in this galaxy. There is a ping pong ball coming. You can see it.
So it was in the cans for just a little bit of time.
Just not bad, right? 4 walls of metal and a little ping pong ball. So that was pretty loud, pretty nice.
Okay, but I don't know about you, Heinrich, but I'm getting tired and thirsty. Are you thirsty?
I think we're getting thirsty.
Okay, so I think we should have a little bit of refreshment here. And what is something cool that we could put into this bottle to make
How
ourselves?
about liquid nitrogen?
Liquid nitrogen. So we're going to put liquid nitrogen into this bottle
Okay.
and see what happens to this liquid nitrogen if we put it into this bottle, okay? So there's some liquid nitrogen in this bottle. Is that enough? No. No, okay. No way? Okay, no way. Is that a way? More, okay, a little bit more, but not too much more. A little bit more, a little bit more. I think we can do a little bit more.
Ooh, that looks good.
Well, I think that might be a little more and a little bit too much. So we're going to pour just a little bit out. Yeah, that's about right. I think that's good.
Perfect. Now, let's go over here.
So now I'm going to take this beverage and I'm going to close off the top. There's liquid nitrogen inside, and we're going to close this off and then dunk it into the
hot water.
Hot water. Oh, what?
Let's see what happens. All right, all right, all right.
Okay.
All right, you guys. This is getting close to the end of the show right now. And so we want to thank a whole bunch of people who made this possible.
So we first want to thank Andrew and Brent. They've been terrific. They helped put this whole show together. And then our high-speed camera operators and who saved us in the middle of the show.
That's right.
Liddy and Jai. Our audio-visual crew up on top who made all of the sound work well. This is Steve Bandick, Warren Friedel, Chris Kilch, and Freddie Peralta. Let's give them a hand. Now, we hope you will all go and see the open house in Demo Alley. That was put together by Sarah King, Justin Geriller, Eileen Shu, and Jeffrey Gustafson.
Good. And by the way, when you're done with this in a few minutes, you should go outside and do partake in these wonderful tours that will get you to us scientists' natural habitat next door. Plus Demo Alley for you, hands-on experiments. And it's all made possible by
these 90 scientist volunteers who have helped put the show together. And we had support from the Department of Physics, the James Franck Institute, our Materials Research Center, and our Vice Presidents for Research. So we thank them all very much. And our staff photographer is Kai To. And so now we want to say goodbye to you.
Yes, let's say goodbye to you. And we do that in style. Okay, Sid?
Okay, so.
Okay.
Are you ready?
Are you ready?
Get set.
And go! All right. Okay. Well, where's Sid? What happened to Sid? Do you see Sid? Where did Sid go?
You're looking for me?
Whoa! Oh, there he is! All right. So thank you all for coming. And now please, if you go outside, there will be tour guides that get you to the demo alley and also to the labs, all right? All right.
So if I take this sheet of paper,
A ordinary liquid, and so there are
Because
this idea of hey. All right.